Okay, so we're going to be going through another exam walkthrough. This will be on gravitational fields, and we'll be going through a question that's from 2022 Jan. So part A says that the planets orbit the sun in approximately circular orbits. The orbital time t of a planet is related to the average distance r of the planet from the sun. Show that the t is related by the expression t squared is directly proportional to r cubed. So if a planet is orbiting the sun and that orbit is a circular orbit, it would look something like this, then we can say the centripetal force is equals to the gravitational force. The centripetal force is equals to mr omega squared, which would be equals to the gravitational force, which is equals to gmm over r squared. The mm cancel out, and we have r omega squared is equals to gmr squared over r squared. And then I'm going to move the r to the other side, and we have omega squared is equals to gm over r cube. We know omega is equals to 2 pi by t, and omega squared will be 4 pi squared by t squared. Okay, so that's what we're going to get. Now, next. So plugging that in, I'm going to get 4 pi squared by t squared is equals to gm by r cube. Cross multiplying it will give me 4 pi squared r cube is equals to gmt. And let me put that t squared over there. And then moving the gm to the other side, I'm going to get t squared is equals to 4 pi squared over gm times r cube. And this is a constant, so we can say this is k. So I'm going to get t squared is equals to kr cube. And that's going to be showing me that t squared is directly proportional to r cube. Alright, now the part 2, which students actually, according to the examiner report, found a little bit difficult to do, and many scored only 2 to 3 marks in this. It says when the planet align as they orbit the sun, they are said to be in opposition. The diagram shows the Earth and Jupiter in opposition. A student states that the Earth and Jupiter are in opposition every 13 months. Okay. And then it says, deduce whether this statement is correct. And they've given me the mean distance from Earth and Jupiter to the sun. So this is the distance from the Earth to the sun, and this is the distance from the Jupiter to the sun. And they've given the time period of Earth. So the time period of Earth, the time taken for Earth to complete one full circular orbit around the Earth square is equals to k times the mean distance from Earth to Sun cube. Okay? And then I can make a similar expression for Jupiter. I can say the time period of Jupiter square is equals to k times the distance from Jupiter to the Sun cube. And I can say te squared over re cube is equals to k. And I can do the same thing with Jupiter as well. And then I can equate both the equations. Okay, and then here I have my equation. What I'm looking to find here is, my main objective is to find the time period of Jupiter. So I'm going to make the time period of Jupiter my subject. So I'm going to get this as my equation, and then I'm going to square root both sides. So now I've plugged in all the values, and if you see, I have taken the time to be in 1 year. When I do this, my final answer of the time period will also be in years. You can also put in months there and you'll get the final answer in months, but I feel like this is a bit easier to plug into the calculator. That's going to give me 18.85 years as the time period for Jupiter. So now I can plug in the time period of Jupiter here into my data. The time period of Jupiter should be 11.857 years, and the time period for Earth should be 1 year. Okay. Now, what's basically going to happen is by the time Earth moves around a full 2 pi, Jupiter would have moved a little bit of distance as well. Okay, so let's calculate how much that distance would be. So, well, actually distance isn't the right word. Once Earth completes a full cycle and it moves through an angular displacement of 2 pi, we can say that Jupiter also had an angular displacement as well. Okay, Because remember, we're not talking about distances, we're talking about things moving in circles, so they're going to be moving angular displacements. Okay, so we know that omega is equals to the angular displacement moved by Earth over time, and omega is also equals to the angular displacement of Jupiter over the time. Okay, and then we know omega is also equal to 2 pi divided by the time period of Earth, and omega is also equals to 2 pi divided by the time period of Jupiter. So I'm going to plug in 1 year into this equation right over here. I'm going to get 2 pi rad per year. And I'm going to plug the value in here as well of the time period of Jupiter. I'm going to get 0.53 rad per year. Okay, so every year Earth is going to be moving 2 pi radians and Jupiter will be moving 0.53 radians. Okay, so let's say after 1 year. So we look at this image after 1 year. What's the image going to be looking like? So if we see this image after 1 year, Earth will be at the same place again because it has moved 360 degrees. It has moved 2 pi as the angular displacement, but Jupiter will be right over here. Okay, and Jupiter would have moved 0.53 radians. So Earth then has to cover this 0.53 radians in order to be in opposition with Jupiter then, which means they are aligned in the same position. So it has to cover this 0.53 radians as well. So Earth has to do two things. So let's say this is A, time A and time B. So time A, let's look at time A, okay? So Earth has to do two things. One, Earth has to cover 2 pi as the angular displacement, and then Earth also has to cover 0.53 extra angular displacement in order to be in opposition with Jupiter. Okay, so I'm going to plug the value in there. Okay, now we know that the omega is equals to theta e over, or the angular displacement, divided by time. So we know that's 2 pi rad per year, and then the angular displacement Earth has to cover is 2 pi plus 0.53, so it can be in opposition with Jupiter. And I'm going to divide that by time, and this time will, remember, be in years. And then I'm going to be finding the value of t, which is going to be 1.0843 years. And I'm going to convert this into months, so I can see how many months will it take for Earth to be in opposition with Jupiter again. So I'm going to times it by 12, and I'm going to get 13.01 months, which is also approximately equals to 13, what was the value? 13 months. So the Pearson is correct, or the statement is correct. Okay, that's the answer. It was a little bit tricky. It used your understanding of circular motion. So hope you understood this. If you have any other doubt, you can ask me. And yeah, there is one more part I forgot. Yeah, let's look at this part as well. Okay, completely forgot that. Okay, so there's one more part as well. Let's do this. Right, so we have the distance from the sun distance of Jupiter from the sun varies from 7.4 times 10 to the power of 11 to 8.2 times 10 to the power of 11. Calculate the change in gravitational potential of Jupiter as it moves from its closest distance to the furthest distance. So this is the sun, and Jupiter is going to move from this distance to this distance. So from distance r1 to distance r2. So from distance r1 to distance r2. So we can say this is point A and this is point B. Now to find the change in GPE, we need to simply do the mass of Jupiter times the change in the gravitational potential. The change in gravitational potential is equals to gravitational potential at B minus gravitational potential at A. That's going to be minus GM over R1 and minus GM over R2. And that's going to give me minus GM over R1 plus GM over R2. And I'm going to factor the GM out, so I'm going to get GM, and then I'm going to get the brackets as minus 1 over R1 plus 1 over R2. Okay, so this will give me the value of change in V. So I'm going to plug in the values. A very important thing to keep in mind is this is the mass of the sun throughout this. mass of sun. This is the mass of sun, okay? A little bit of a mistake. This should be the other way around. So this should be R2 here and R1 because it's the potential at B. So kind of didn't realize that when I was plugging in the values of R1 and R2. Right, so that's how it's supposed to be, okay? Well, either way, let's find the answer now. That's going to give me 1.76 times 10 to the raised power of 7 joule per kg. And I'm going to then multiply this by the mass of Jupiter. That's going to be 1.9 times 10 to the raised power of 27 kg. And that's going to give me 3.34 times 10 to the raised power of 34 joules, okay? Right, so be careful with the values. I also messed up a little bit there. But yeah, so be careful with the values. Make sure you know what mass of sun is and what is the mass of Jupiter here in the equations. And this question is actually quite repetitive, so make sure you score these marks. Here is the mark scheme. The examiner report.